Chapter 10, Carboxylic acid and its derivative. 10.4 Preparation of carboxylic acid. At the end of the lesson, the students should be able to explain the preparation of carboxylic acid through oxidation of alkylbenzene, alcohol and aldehydes, hydrolysis of Nitrile compounds, carbonation of Grignard reagents. Carboxylic acid can be prepared by first methods, oxidation of alkylbenzene. Second methods, oxidation of primary alcohol. Third methods, oxidation of aldehydes. Fourth methods, hydrolysis of Nitrile compounds. The fifth method is carbonation of Grignard reagents. Oxidation of alkylbenzenes. Students already learned this in chapter 6, benzene and its derivative. The reactant is alkylbenzene with benzylic hydrogens. We're using a strong oxidizing agent here, hot acidified potassium permanganate, hot acidified potassium dichromate or sodium dichromate, chromic acid. So you can see here from the equation, the general equations, alkyl group which is the R with benzylic hydrogens attached to the benzene ring, regardless their change length is converted to COH, as long as you must have one benzylic hydrogens in alkyl groups attached to benzene ring, it will convert it to COH. Okay, we look at the first example. Toluene undergo oxidation. On the alkyl group here, the CH3, you have 3 benzylic hydrogen. The carbon that directly attached to benzene ring is called benzylic carbon, and the hydrogen that directly attached to benzylic carbon is called benzylic hydrogens. So the metal group here will be that converted to COH. Benzoic acid, you get benzoic acid and water. So for the second example here, we have 3 benzylic hydrogen on the left and we have 2 benzylic hydrogen on the right. Undergoes oxidation. 1 ethyl 4-methylbenzene will be converted to 1,4-benzene dicarboxylic acid. So you can see both sides you get COH, and the byproduct is carbon dioxide. Why? Because the side chain here you have more than 1 carbon, so you get carbon dioxide and water. For the third example here, there's no reaction. Why? Because benzylic carbon here don't have any benzylic hydrogens, so the protylbenzene does not undergo oxidation, no reactions. Okay, now we look at the second methods. Oxidation of primary alcohol. Primary alcohol are oxidized to aldehydes, and further oxidation will give a carboxylic acid. So firstly, primary alcohol oxidation get aldehydes, further you get carboxylic acid. So if you use strong oxidizing agents, directly from primary alcohol we will get carboxylic acid. So look at the example here, ethanol. Using strong oxidizing agents, ethanol will be converted to ethanoic acid. So the CH2OH will be converted to COH. So you can see here all of them is primary alcohol. The first one we're using chromic acid. So the CH2OH here will be converted to COH. So from primary alcohol you get carboxylic acid. Same also, primary alcohol here you get carboxylic acid also. This is called benzoic acid. Primary alcohol using strong oxidizing agent we get carboxylic acid also. Now we look at the third methods, oxidation of aldehydes. Aldehydes are easily oxidized to carboxylic acid by using strong oxidizing agent. So this is a strong oxidizing agent here. So aldehydes, you can see the carbonyl group here, the COOH, will be oxidized to COH, carboxylic acid. So the CHO here, the aldehyde, the COOH, the carbonyl groups for aldehydes will be converted to COH. So for aldehydes, we get carboxylic acid using strong oxidizing agent. So using strong oxidizing agent, all of them is aldehydes. So the aldehyde part here, the COOH, carbonyl groups, will be converted to COH, carboxyl groups. So for aldehyde, you get carboxylic acid. Second example is the same. The COOH, carbon groups for aldehydes, we will convert it to COH. Carbon groups converted to COH. So from aldehydes, we're using strong oxidizing agents, we get carboxylic acid. Okay, now we look at the third methods, hydrolysis of natural compounds. Starting from haloalkane or alkyl halides, react with KCN in ethanol heat or NaCN in ethanol heat. The haloalkanes will be converted to natural compounds, RCN. The natural compounds can undergo acidic hydrolysis, HO plus in hot condition or H plus H2 heat, we get carboxylic acid and ammonium ions. You can see here the cyano groups will be converted to carboxyl groups. So from natural compounds we get carboxylic acid. If the natural compounds undergo basic hydrolysis, OH minus water heat, we get carboxylic ion. You can see here the cyano groups will be converted to COO minus. If the carboxylic ions with ammonia react with acid, we will get carboxylic acid and ammonium ions. Okay, look at the example, propanenitrile, acidic medium or acidic hydrolysis. The cyano groups will be converted to carboxyl groups. So for propanenitrile, we get propanic acid. The byproduct is ammonium ions. Using the same reactants, undergo basic hydrolysis. The cyano groups will be converted to C11O O minus, which is a carboxylic ions, plus the byproduct is ammonia. We look at the third example, cyclopentane carbononitrile. The CN undergo basic hydrolysis because NaOH is a strong base. So the CN will be converted to C11O O minus. Because we're using NaOH, you have Na plus, so you have Na plus here. The byproduct is ammonia. Sodium cyclopentyl metanoate is a salt. React with acid, so you convert it to cyclopentyl metanoic acid plus ammonium ions. Okay, now we look at the fifth methods, carbonation of Grignard reagents. Grignard reagents react with carbon dioxide followed by hydrolysis produce carboxylic acid. So starting from haloalkanes, react with Mg dry ether, we get Grignard reagents. The Grignard reagents react with the first step, carbon dioxide, second step, hydrolysis, acidified hydrolysis, we get carboxylic acid plus byproduct MgOHX. We can separate it into two steps. The first step here you can see react with carbon dioxide, we get an intermediate. So here is ionic bond. Here's ionic bond here. The intermediate it will react with acidified water. So hydrolysis, you get carboxylic acid plus MgOHX. So you can see here the R does not change. The R group does not change. The changes happens to the X, the halogens converted to MgX, then further to COH. So you have two steps here. So RCOH produced has one carbon atoms more than the initial haloalkanes and Grignard reagents. Okay, now we look at the given example. The bromoethanes, which is haloalkanes, react with Mg dry ether. We get ethyl magnesium bromide, which is a Grignard reagents. So the Br will be converted to MgBr. So the Grignard reagents react with carbon dioxide first step, second step, acidic hydrolysis, you get propanic acid, which is carboxylic acid. So the MgBr will be converted to COH. This is byproduct. We look at the fourth example here, same also. 2-chloroputane react with Mg dry ether. So you get sec potassium magnesium chloride, which is the Grignard agents. So first step, carbon dioxide. Second step, acid hydrolysis. You get 2-methyl-pentanone acid. So from haloalkanes, we got Cl. MG reactor, we get MgCl. Then first step, carbon dioxide. Second step, H2O+, you get COH. So which is carboxylic acid.
Thank you for watching.